Hey friends, welcome back. 20 new questions today. This one's all about AI search hybrid retrieval, RAG chunking trade-offs, and serving tier economics. Standard drill. Question. 10-second timer. Answer. Explanation. Pause whenever you need to think. Good luck. Now, question 1. Identify the business need first. A generative AI engineer is building a search system for an internal developer portal. Engineers frequently search using exact error codes and API method names, but also ask conceptual questions about architecture patterns. Semantic-only search misses exact token matches, and keyword-only search misses conceptual intent. Which AI search configuration handles both query types with a single index? Select one. Review the answer choices on screen. The correct answer is option A. Two separate indexes sounds logical. Here is why it loses. Hybrid search in Databricks AI Search combines BM25 keyword scoring with semantic vector similarity in a single index, and merges the two ranked lists using Reciprocal Rank Fusion, RRF. BM25 excels at matching exact terms like error codes and API method names, while semantic search captures conceptual intent and paraphrased queries. RRF merges both rankings without requiring manual score normalization, producing a single ranked result set. Semantic chunking with smaller chunks changes how documents are split rather than how they are searched, adding no keyword matching capability. Maintaining two separate indexes doubles infrastructure overhead and adds query latency while missing the integrated RRF scoring that native hybrid search provides. Pre-normalized embeddings enable cosine similarity distance measurement, but address only the vector component and provide no keyword matching capability on their own. Now, question 2. This is a precision check. A generative AI engineer at Bridgewater Analytics is integrating MLflow's built-in LLM judge into a RAG evaluation pipeline to score whether retrieved document chunks are relevant to each user query. A stakeholder asks the engineer to explain how the scoring system works. Which description accurately reflects the built-in LLM judge's relevant scoring approach? Select one. Review the answer choices on screen. The correct answer is option B. This question turns on one specific number. What is it? MLflow's built-in LLM judge uses a 4-point relevance scale ranging from 0 to 3. A score of 0 indicates the retrieved chunk is not relevant to the query, 1 indicates partial relevance, 2 indicates relevance, and 3 indicates high relevance. This graded scale captures meaningful distinctions between degrees of relevance rather than treating retrieval as a binary pass or fail. A continuous 0.0 to 1.0 score calibrated against human labels describes a different evaluation methodology and does not reflect how the built-in judge operates. A binary 0 or 1 scale cannot express the nuanced difference between partial and full relevance that the 4-point system provides. A 5-point scale starting at 1 does not match the documented implementation and would eliminate the explicit representation of completely non-relevant results at score 0. Let's pause here. The MLflow scoring scale question is one the exam loves to flip on you. Picture a legal firm with 10,000 case documents loaded into a RAG chatbot. When a lawyer asks a question, the system pulls 5 chunks. You need to score each one, not just pass/fail, but how relevant it is. MLflow's built-in judge does exactly this. It sends each chunk to an LLM grader that returns a number from 0 to 3. 0 means completely irrelevant, 1 means partial relevance, 2 means relevant, 3 means highly relevant. A direct hit. The big trap is the 5-point scale starting at 1. That scale has no 0, so there's no way to flag a chunk as totally off topic. The 0 matters. The exam rewards knowing it's a 4-point scale, starting at 0, not 1. Now, This is question 3. A generative AI engineer has been running RAG configuration experiments and logging results as MLflow logged models. They select the best performing configuration and want to share it with model owners across the organization, who need to see all historical performance metrics alongside the registered model artifact in a single view. What should they do? Select 1. Review the answer choices on screen. The correct answer is option D. Promotion is additive. All the performance data travels with the model. When a logged model is promoted to a Unity Catalog model version, all metrics, parameters, and traces captured during the experiment automatically appear on the model version page in the registry. This gives model owners a single unified view of the artifact and its full performance history without any manual data transfer or additional tooling. Exporting metrics to a CSV creates a static snapshot that is disconnected from the live registry and requires manual maintenance each time experiments are updated. Copying a run ID into a description field provides a text reference but delivers no structured access to performance data within the registry interface. Stakeholders must navigate elsewhere to find the data. Creating a new experiment to log fresh metrics produces a separate record unlinked to the original experimental history, losing the comparative data from earlier configurations that informed the selection decision. Time for another one. Question 4. Classic exam trap. A generative AI engineer at Greenfield AI is designing an evaluation suite for a medical document retrieval system. The team needs to measure 2 separate dimensions of retrieval quality: whether all clinically relevant documents are captured in the results, and whether the most relevant documents are ranked at the top. Which 2 MLflow built-in retrieval metrics should they include? Select 2. Review the answer choices on screen. The correct answers are option A and option B. 2 requirements, 2 metrics. Do not overselect or underselect. Recall _@_k measures completeness, the fraction of all known relevant documents that appear in the top K retrieved results, directly addressing the requirement to ensure no clinically relevant documents are missed. NDCG _@_k measures ranking quality with a score from 0 to 1, where 1.0 represents perfect ordering of relevant documents. It rewards systems that surface the most important documents earliest in the result list, addressing the ranking dimension. Together, these 2 metrics cover both stated requirements. Precision _@_k measures how many retrieved documents are relevant, but does not quantify completeness of recall or the ordering of results, so it addresses neither stated requirement on its own. Execution _time _ms is a latency field in the inference table schema, and is not a retrieval quality metric available through MLflow's built-in evaluation functions. Sampling _fraction is an inference table configuration parameter controlling logging volume, not a retrieval quality measurement. Time for another one. Question 5. Look for the constraint that matters. A generative AI engineer is designing a RAG system for a legal research firm, where retrieval must precisely identify the specific clause being referenced, but LLM generation requires surrounding paragraph context to produce useful summaries. Which chunking architecture best addresses both requirements simultaneously? Select 1. Review the answer choices on screen. The correct answer is option D. Clause precision versus paragraph context. What resolves both simultaneously? The parent-child retrieval pattern directly resolves the conflict between precise retrieval and broad generation context. Small chunks of around 512 tokens allow the vector search to pinpoint the specific clause the user is referencing. Once the relevant small chunk is identified, its parent segment of around 2048 tokens is passed to the LLM, providing the surrounding paragraph context needed for coherent summaries. Semantic chunking produces topically coherent chunks, but uses a single granularity for both retrieval and generation, leaving the mismatch unresolved. Fixed-size chunking with overlap is also a single chunk size strategy that cannot simultaneously optimize for clause-level precision and paragraph-level context. Recursive splitting preserves structural boundaries, but still uses one chunk size for both stages. The first 6 questions hit hybrid search with RRF, parent-child chunking for retrieval generation tension, and MLflow logged model promotion. All 3 carry the same lesson: the integrated approach beats the manual workaround. Time for another one. Let's read question 6. A generative AI engineer at Meridian AI has been iterating on a document classification pipeline using MLflow 3, logging dozens of experiment runs as logged models with associated metrics, parameters, and traces. The team selects the best run and promotes it to Unity Catalog to enable governance and production deployment. What happens to the captured performance data when the logged model is promoted to a Unity Catalog model version? Select one. Review the answer choices on screen. The correct answer is option B. Logged model objects carry their full history on promotion. In MLflow 3, logged models automatically capture metrics, parameters, and traces throughout all development phases. When a logged model is promoted to a Unity Catalog model version, all of that accumulated performance history carries forward and becomes visible directly on the UC model version page, linking development evidence to the governed artifact. Metrics and parameters are not scoped exclusively to an experiment in a way that prevents them from traveling with the model. The logged model object carries its own complete performance record. There is no requirement to relog anything manually after promotion. The promotion step transfers the full record alongside the artifact. Logged models are not converted to experiment runs on promotion. They are distinct entities in the MLflow 3 object hierarchy and retain their identity when registered to Unity Catalog. Ready. Question 7 is next. Quick check. A generative AI engineer is building a product search feature for a large electronics retailer. Users frequently search with exact model numbers like UX 9924K alongside natural language descriptions like wireless noise-canceling headphones under $200. The team needs a single retrieval configuration that handles both query styles accurately. Which AI search configuration meets this requirement? Select one. Review the answer choices on screen. The correct answer is option C. Same hybrid pattern, different product domain. One index wins. Hybrid search in Databricks AI Search combines OCopy BM25 keyword matching for exact term precision with vector similarity for semantic relevance, and fuses both rankings using Reciprocal Rank Fusion with a default RRF_param of 60. This single index handles both exact product code lookups and natural language queries accurately in one configuration. Maintaining 2 separate indexes adds operational complexity and requires custom application-level result merging without the benefit of unified RRF ranking. An ANN-only index fundamentally lacks keyword matching, and increasing the number of retrieved results does not recover exact term hits that were never ranked at all. BM25-only indexing handles model number lookups well, but fails to capture semantic intent for natural language queries describing product characteristics. Let us switch gears. Slow down for question 8. A generative AI engineer at Fabricom is building a proof-of-concept internal HR chatbot using the foundation model API. Traffic is expected to be sparse and unpredictable over the first 4 weeks of development. The engineer wants to minimize cost and operational overhead during this phase. Which serving approach is most appropriate? Select one. Review the answer choices on screen. The correct answer is option A. Sparse proof of concept traffic changes the cost math entirely. Pay-per-token serving is the Databricks recommended approach for early-stage development and exploratory work where traffic is low or unpredictable. Charges apply only to tokens actually consumed, which keeps costs minimal when request volume is sparse or irregular. Provisioned throughput is recommended for production workloads with predictable, sustained demand because it reserves dedicated compute capacity. For a proof of concept with low traffic, that reserved capacity sits idle and generates unnecessary charges. Setting min_provisioned_ throughput to 0 is not a supported zero-cost configuration in the provisioned throughput model. The minimum allocation still incurs capacity charges proportional to the reserved token rate. Deploying a custom model on a single node cluster introduces significant operational overhead for infrastructure management, defeating the purpose of a managed serving endpoint during exploratory development. Let us switch gears. Question 9. The scenario tells you the trade-off. A generative AI engineer Advantage Analytics is building a document retrieval system where all documents are chunked to a maximum of 256 tokens. Cost and latency are the primary constraints. 4 embedding models are available. Which model should the engineer choose? Select one. Review the answer choices on screen. The correct answer is option B. Context window just covers the chunk ceiling. Go smallest. When cost and latency outweigh quality as constraints, the optimal embedding model is the smallest one whose context length still covers the maximum chunk size. A context length of 256 tokens exactly matches the chunk ceiling, ensuring no content is truncated, while the 0.13 GB model footprint and 384-dimensional output represent the smallest and fastest option available. Smaller embedding dimensions also reduce vector storage costs in the index. A 512-token context window is larger than necessary for chunks that never exceed 256 tokens, and the greater model size and higher embedding dimension add compute cost and latency with no retrieval benefit. The 7 GB and 11 GB models provide far more context capacity than the chunks require, while dramatically increasing inference cost and embedding storage, directly contradicting the stated priorities. Keep your focus here. Question 10. One detail changes the answer. A generative AI engineer at Thornbridge e-commerce is building a product search system using Databricks AI Search. Their search interface requires showing paginated results with up to 500 products per query when users browse categories. The engineer plans to use hybrid keyword similarity search to combine lexical and semantic matching for better relevance. What limitation must the engineer account for when designing this system? Select one. Review the answer choices on screen. The correct answer is option B. Hybrid and full-text search share a hard per-query result ceiling. Hybrid and full-text search queries in Databricks AI Search are hard capped at 200 results per query, whereas pure ANN vector similarity queries support up to 10,000 results. A design requiring 500 products per page via hybrid search directly exceeds this limit, forcing the engineer to redesign pagination or fall back to ANN-only queries for large result pages. The approximately 320 million vector ceiling is a corpus size constraint on standard endpoints, not a per-query result limit. Change data feed must be enabled, not disabled, for delta sync indexes to track incremental changes. The 128 concurrent request limit governs how many simultaneous requests an endpoint handles at once, which is a throughput constraint entirely separate from the number of results per query. This one trips up engineers who know hybrid search is better, but miss the hidden result limit. Imagine you're building a category browse page that shows 500 products at once. Sounds reasonable for e-commerce, but Databricks AI Search has a hard cap you need to know. Hybrid search blends keyword and semantic matching, great for relevance, but it caps at 200 results per query. Full stop. Pure ANN search, the vector-only mode, can return up to 10,000, so 500 per page works fine with ANN, but it blows past the hybrid limit. The engineer picked hybrid for relevance. Smart choice, except 500 exceeds 200. You'd need to shrink your page size or switch modes for large result sets. The question rewards knowing the 200 hybrid cap, not anything about corpus size or request limits. The middle block surfaced 3 hard limits: the 200 result cap on hybrid queries, AI Search's L2 only metric requiring vector normalization for cosine ranking, and pay per token for sparse workloads. Keep your focus here. Question 11. Find what the distractors miss. A generative AI engineer at an academic publishing platform is building a research paper discovery tool using Databricks AI Search. The team's retrieval quality evaluations show that raw similarity scores produce counterintuitive ranking behavior when comparing long and short abstracts. The team decides to switch from L2 distance-based ranking to cosine similarity-based ranking. What must the engineer do to the document embeddings to achieve cosine similarity within AI Search? Select one. Review the answer choices on screen. The correct answer is option D. There is no distance metric config. The trick is normalization. Databricks AI Search exclusively uses the L2 Euclidean distance metric computed by the HNSW algorithm, and this metric cannot be changed through configuration. When all vectors are normalized to unit length before indexing, the L2 distance between two unit vectors is a monotonic function of their cosine similarity, so the ranking order produced is identical to cosine similarity ranking. Pre-normalizing embeddings before indexing is therefore the correct and only supported approach. There is no distance_metric parameter available when creating an AI search index. Enabling hybrid search adds BM25 keyword retrieval to the pipeline, but does not alter how the semantic retrieval component computes distances between vectors. Direct access indexes allow callers to supply their own pre-computed embeddings, but use the same HNSW algorithm with L2 distance. Switching index type does not expose an alternative distance metric. This one is sneaky. The answer isn't in any config screen. Let's look at the math. Imagine comparing a 2,000-word paper abstract to a 150-word summary. Longer texts tend to produce bigger embedding vectors, which skews L2 distance rankings. You want cosine similarity instead. It ignores vector length entirely. Here's the catch. Databricks AI Search doesn't let you pick a distance metric. It's always L2. Locked in. But there's a neat math trick. Normalize every embedding to unit length before indexing. Normalizing removes the length effect entirely. Then L2 distance and cosine similarity rank results the same way. The exam rewards fixing your data before indexing, not hunting for a config option that doesn't exist. All right. Question 12. Separate context from noise. A generative AI engineer at Castleton AI enabled inference tables on a production model serving endpoint 6 weeks ago. The table was successfully capturing request and response payloads. After a routine governance review, the data engineering team renamed the Unity Catalog table to follow the company's new naming convention. The following day, the engineer notices that no new rows have been written to the renamed table. What is the most likely cause and how should the engineer resolve it? Select one. Review the answer choices on screen. The correct answer is option C. A routine governance rename can silently break inference logging. Inference tables stop logging when the referenced Unity Catalog table is renamed. When the table schema is changed, or when the table is deleted. When the data engineering team renamed the table, the serving endpoint retained a reference to the original name, which no longer exists, causing all subsequent logging to cease. The resolution is to reconfigure the inference table setting on the serving endpoint to point to the new table name, which creates a fresh table at that path and resumes logging. Inference tables do not have a time-based pause mechanism and continue operating indefinitely as long as the reference table remains intact and accessible. The 10 MB payload limit causes individual oversized payloads to be skipped, not a wholesale suspension of all logging activity. Inference table logging behavior is not coupled to endpoint scaling events. Every qualifying request is logged regardless of whether the endpoint is scaling up or running at steady state. Alright, question 13. Compare scope and condition. A generative AI engineer at Keystone AI is building a real-time product availability assistant. They have published inventory features to an online feature store and are attempting to deploy a feature-serving endpoint on a cluster running Databricks Runtime 13.3 ML with Databricks Feature Engineering version 0.1.1 installed. The deployment fails. Which two conditions are causing the failure? Select 2. Review the answer choices on screen. The correct answers are option A and option C. 2 hard version gates, both must be true simultaneously. 2 hard prerequisites are unmet in this scenario. Feature serving requires Databricks Runtime 14.2 ML or higher, so running on 13.3 ML falls below the threshold and prevents the endpoint from initializing. Additionally, the Databricks Feature Engineering library must be at version 0.1.2 or higher. Version 0.1.1 lacks the necessary client-side APIs for feature serving and causes the deployment to fail during library validation. GPU acceleration is not a requirement for feature serving. It operates on standard CPU clusters. Online feature store tables do not need to be exported to DBFS. They are published to an online store that the endpoint queries directly at inference time. There is no dedicated high-memory instance type requirement documented for feature-serving endpoints. This deployment failure question has 2 real answers. Let me show you exactly what breaks and why. Imagine you spent all afternoon wiring up a real-time inventory assistant, hit deploy, and got a wall of errors. Where do you start? Think of feature serving like a car that needs 2 keys to start. Both must turn before anything moves. Key 1. Your cluster must run Databricks Runtime 14.2 ML or higher. Version 13.3 is too old. Key 2. The Databricks Feature Engineering library must be at version 0.1.2 or higher. Version 0.1.1 is missing the client code that feature serving needs. The exam also drops in 3 fake blockers. GPU clusters don't matter. File exports aren't needed. Special memory isn't required. The question rewards knowing the 2 version gates. Alright, let's handle question 14. A generative AI engineer is reviewing the monitoring dashboard for a provisioned throughput foundation model endpoint that has been live for 2 weeks. The team wants to verify whether the endpoint is operating within its allocated capacity. Which metric should they examine to assess provisioned throughput utilization? Select 1. Review the answer choices on screen. The correct answer is option C. Provisioned throughput capacity maps to exactly 1 metric. For provisioned throughput endpoints, tokens per second is the primary capacity metric. It reflects how much of the provisioned throughput the endpoint is consuming and directly indicates whether the allocation is correctly sized for current traffic. When tokens per second approach the provisioned maximum, the endpoint risks throttling and response degradation. When they remain well below the maximum, the allocation may be oversized and unnecessarily expensive. CPU utilization is not a user-facing metric for managed model-serving endpoints, because the compute infrastructure is abstracted away. Mean time between failures derived from inference table status codes is a reliability signal, not a capacity measurement. Embedding vector count per minute is relevant only to embedding model endpoints, not to provisioned throughput generative model endpoints. Here we go. For question 15, the qualifier matters. A generative AI engineer is deploying a customer-facing legal inquiry chatbot through AI Gateway. The compliance team mandates that social security numbers, email addresses, and phone numbers must never be transmitted to or returned from the underlying LLM. Any request or response containing these data types must be rejected entirely, not modified. Which AI Gateway guardrail configuration meets this requirement? Select one. Review the answer choices on screen. The correct answer is option C. The phrase rejected entirely, not modified eliminates two options instantly. Configuring PII detection with the block action on both requests and responses ensures that any payload containing social security numbers, email addresses, or phone numbers is rejected outright before it reaches the model or the user. This prevents PII from transiting through the system in either direction, satisfying the compliance mandate completely. Redaction replaces PII with placeholders rather than rejecting the request, which means the content is still processed by the model and does not meet the requirement to stop transmission entirely. Safety filters address content categories like hate speech and violence, not personally identifiable information, and rate limiting reduces request volume without inspecting content for PII. Monitoring inference tables is post hoc detection that occurs after PII has already been transmitted, directly violating the compliance requirement. The third block linked operational details, a UC rename silently breaks inference logging. Feature serving has two minimum version gates, and recall at K is the only metric that directly penalizes missed relevant documents. Here we go. Question 16. Solve the situation, not the keyword. A generative AI engineer is designing the evaluation strategy for a clinical decision support (RAG) system used by emergency physicians. For each patient query, multiple relevant clinical guidelines may exist. The team's primary concern is ensuring no relevant guideline is missed. A false negative is considered far more harmful than retrieving an extra irrelevant document. Which retrieval metric should guide optimization? Select one. Review the answer choices on screen. The correct answer is option B. When a missed document could harm a patient, one metric owns that. Recall at K directly measures what percentage of all known relevant documents appear within the top K retrieved results, making it the metric that explicitly penalizes missed relevant documents. When false negatives are more dangerous than false positives, as in a clinical context where a missed guideline could harm a patient, recall at K is the correct primary optimization objective. Precision at K measures how many of the retrieved documents are relevant, but does not penalize for relevant documents that were not surfaced, ignoring the exact failure mode the team is trying to prevent. NDCG at K and DCG at 10 both evaluate ranking quality and relevance intensity, which are valuable secondary metrics, but they do not directly quantify how many relevant guidelines the system failed to retrieve at all. Next up, question 17. Picture the scenario first. A generative AI engineer at Silvergate Insurance is configuring a feature spec for a real-time premium pricing endpoint. The application needs two types of values at inference time: a risk score that has already been computed and stored in an online feature store table keyed by policy ID, and a loss ratio that must be calculated on the fly by dividing reported losses by earned premiums, both of which arrive as fields in the incoming request. Which combination of feature spec components should the engineer use? Select one. Review the answer choices on screen. correct answer is option B. One component fetches stored values, the other computes from request fields. Feature lookup is designed for retrieving pre-materialized feature values from an online feature store table using a lookup key such as policy ID. Feature function is designed for applying transformations to values available at inference time, such as computing a ratio from two fields included in the incoming request. Combining both components in the same feature spec handles the pre-materialized lookup and the on-demand computation in a single unified specification. Using two feature lookup components requires both values to be pre-computed and stored in online tables. It cannot perform on-the-fly arithmetic from request fields. Using two feature function components is incorrect because feature function does not retrieve values from an online store. It only applies transformations to inputs already available at call time. A single feature lookup cannot execute derived computations on request fields. It is limited to fetching stored values by key. Let's slow down here. Feature lookup and feature function look similar, but they do completely different jobs. Imagine your insurance app gets a request with a policy ID plus two numbers, reported losses and earned premiums. You need a risk score, already saved in a database, and a loss ratio you have to calculate right now. Those are two different jobs. Say policy 8847 has a risk score of 0.73 stored in your online feature store. Feature lookup grabs that by key. Fast, no math. But the loss ratio isn't stored anywhere. It's just losses divided by premiums, both arriving in the request. Feature function computes that on the spot. The trap here: thinking one component does both. Feature lookup only fetches. Feature function only computes. Combine them in one feature spec. That's answer B. Here we go. Let's work question 18. Quick check. A generative AI engineer at Elmwood Analytics is building a RAG application over long technical specification documents. During evaluation, the engineer observes that large chunks improve answer quality because the LLM has sufficient context, but retrieval recall drops because the chunks are too broad to match specific queries precisely. Which chunking strategy resolves this trade-off? Select one. Review the answer choices on screen. The correct answer is option B. Parent-child again, same pattern, long technical documents this time. Parent-child retrieval is specifically designed to resolve the precision versus context trade-off. Small child chunks of approximately 512 tokens are embedded and matched against queries, giving the retriever a precise target. When a child chunk is selected, the system fetches its larger 2048 token parent segment and passes that to the LLM, providing the broader surrounding context the model needs to generate accurate answers. Fixed-size chunking at 2048 tokens embeds the same oversized units that are used for retrieval, so the embedding must represent too much content to match specific queries, while preserving the original recall problem. Semantic chunking groups text by topic similarity and uses those same segments for both retrieval and generation. While semantically coherent, the resulting chunks can still be large and imprecise depending on topic boundaries. Recursive splitting at 256 tokens with no overlap produces highly precise retrieval units, but starves the LLM of surrounding context, which is exactly the generation quality problem the engineer is trying to solve. Now, question 19. Reason from the scenario. A fintech company deployed a foundation model API endpoint with pay-per-token pricing for their financial analysis assistant. Over 3 months, usage has stabilized at approximately 2 million tokens per hour consistently throughout business hours. Inference costs are scaling linearly, and the team wants to optimize spend without compromising the sub-second latency requirement. What serving change should they make? Select one. Review the answer choices on screen. The correct answer is option D. 2 million tokens per hour sustained. The crossover has been reached. At sustained high throughput of 2 million tokens per hour throughout business hours, provisioned throughput becomes more cost-effective than pay-per-token pricing. Provisioned throughput allocates dedicated compute capacity and provides consistent, predictable latency suitable for the sub-second requirement, while eliminating the per-token cost that scales linearly with volume. Pay-per-token is optimal for variable or low-volume workloads where dedicated compute would sit idle. Reducing system prompt length marginally decreases per-call token cost, but does not change the fundamental pricing model mismatch, and risks degrading financial analysis quality by removing necessary context. Application layer request batching reduces the number of API round trips, but does not reduce total token volume and introduces queuing latency that conflicts with the sub-second requirement. Deploying a custom smaller model introduces significant operational overhead for infrastructure management, scaling, and quality validation that may not justify the cost savings for a latency-sensitive production application. Now, question 20. Map the qualifier to the answer. A generative AI engineer at Conteso Insurance is configuring an AI gateway endpoint for a claims processing assistant. Regulatory requirements prohibit customer social security numbers and phone numbers from ever being transmitted to the underlying LLM. Which guardrail configuration meets this requirement? Select one. Review the answer choices on screen. The correct answer is option C. Block stops transmission entirely. Redaction still forwards to the model. PII blocking rejects the entire request when personally identifiable information, such as SSNs or phone numbers, is detected, ensuring that data never reaches the underlying LLM. This satisfies a hard regulatory requirement that prohibits transmission. PII redaction replaces detected values with placeholder tokens, and then forwards the modified request to the model, which still constitutes a transmission event and may not catch every edge case. Safety filtering targets categories like hate speech, insults, and violence, and is not designed to detect structured personal identifiers such as SSNs or phone numbers. Rate limiting controls query volume but does not inspect content for PII, leaving sensitive data free to pass through unrestricted. 3 takeaways from this session. First, AI search hybrid mode merges BM25 and vector rankings via RRF. 2 separate indexes only add overhead. Second, parent-child chunking decouples retrieval granularity from LLM context size, resolving the precision versus breadth conflict directly. Third, provision throughput outperforms pay per token only at sustained high volume. Sparse workloads always favor pay per token. 3 layers: retrieval, evaluation, serving. Every question in this set touched one of them. Lock down the mechanics at each layer and the right answer surfaces itself, on the exam and in production.